Hello everybody, once again. My name is Paweł Gora. I'm a researcher, a PhD candidate at the Faculty of Mathematics, Informatics and Mechanics at the University of Warsaw in Poland. I'm also founder and CEO of the Quantum AI Foundation and the board member of QWORD and QPoland. So both the Quantum AI Foundation and QWORD are non-profit organizations supporting research, education, and collaboration in new technologies, especially quantum computing. All right, but today I will tell you about solving vehicle routing problems using quantum computing. That's the agenda for today. So first I will define what exactly is the vehicle routing problem, and I will also define some of its variants. I believe that some of you might have already heard about it, but for some people it might be something new. And later I will tell about some quantum annealing approaches to solve this vehicle routing problem. So first I will explain the quantum annealing process, and later I will introduce the so-called Cuba quadratic unconstrained binary optimization formulations and solvers on how to so just to present how we can solve this vehicle routing problem using quantum annealing. And finally, I will tell about the experiments and results of experiments that we've carried out within the GLAD project funded by the European Union. And finally, at the end, I will tell about some plans for the future research. So in fact, some of these plans are already ongoing research because I'm already collaborating with almost 20 people from many countries. So I will later, at the end, I will tell you what we are trying to do now. So what's next? So okay, let's start with the definition of the vehicle routing problem. So we have a directed graph with some non-negative costs assigned to edges, right? So in some nodes of this graph, we have, let's say, our customers that we would like to visit. Then we have the definition of the traveling salesman problem, right? So we have these n selected vertices in the graph. So this can be our customers. And now the question is, what's the shortest possible route that visits all of them and returns to the original vertex, so to the depot, right? So that's the traveling salesman problem. There is also a generalization of the traveling salesman problem that is called the vehicle routing problem, or VRP in short. So again, we also have these n selected vertices in our graph, so we can consider them as our customers. But now the question is, what's the optimal set of up to m routes that visit all selected vertices and start and end in the depot, right? So in this case, it is allowed to just return to the depot and start another route, or we can just try to visit the customers, the nodes from different routes simultaneously at the same time. But for this, we may just need many vehicles to do it, right? Okay, so this is just an example of a solution for the vehicle routing problem. So we have the depot, which is this white square in the center, and we have 3 routes covering all the nodes with customers in our graph, right? So this is just an example of a solution for the instance of the vehicle routing problem, in which we may use up to 3 vehicles, let's say. So it's also good to know that there might be some further extensions of the vehicle routing problem that are more realistic, let's say, or closer to the real world conditions, like capacitated vehicle routing problem. So this is standard VRP, but with limited capacities of vehicles, right? So in the standard VRP, we don't assume that we have some limits, but here we assume that there are limits for the capacities. And there might be also CVRP with time windows. So in this case, we have both the bounded capacities of vehicles, and also we have some time windows in which our customers, so these nodes in the graph, should be visited by any of the vehicles that we have in our fleet. And the interesting and important thing is that all these problems are NP-hard. So most likely we'll not be able to find the most optimal solutions in a reasonable time, in polynomial time, on classical computers. And as we will see, there is a hope that quantum computing may help us solve this kind of problems faster. And why we have such a hope? TSP, so traveling salesman problem and vehicle routing problem, are just examples of the so-called combinatorial optimization problems. So the combinatorial optimization problems are, let's say, optimization problems or computational problems in which we search for the best of many possible combinations. So, for example, we may ask, should I ship this package on this truck or the next one? Or what's the most efficient route a traveling salesperson should take to visit different cities, right? So these are just examples of questions that we ask in case of the combinatorial optimization problems. And it turns out that the physics can help solve these sorts of problems because we can frame them as energy minimization problems. And a fundamental rule of physics is that everything tends to seek a minimum energy state. So, for example, objects slide down hills, how things cool down over time, and this behavior is also true in the world of quantum physics. And now we can use something that is called quantum annealing that simply uses this quantum physics law, the laws of quantum physics, to find the low energy states of a problem. And so now the whole idea is that these low energy states should correspond of a physical quantum system should correspond to optimal or near optimal solutions for our optimization problem. So now the question is how to define our optimization problem as the problem of minimizing or finding the low energy states of our physical quantum system. And now, so I will just tell you how we can do it. But I will tell about it later. But first, assuming that we can define our optimization problem in terms of minimizing or finding the low energy states of our quantum physical system, we can employ the laws of physics to just find these low energy states, and that could correspond to the optimal or near optimal solutions for our optimization problems. And the whole idea comes from something that is called the adiabatic optimization or the adiabatic process. So the adiabatic process in physics is a process that does not involve the transfer of heat or matter into or out of a thermodynamic system. So the energy can be transferred to the surroundings only as work. So, and now here we have the idea behind the adiabatic quantum computing. So first, a potentially complicated Hamiltonian is found whose ground state describes the solution to the problem of interest. So here I used another word that might be unknown for some of you, Hamiltonian. So Hamiltonian is also a concept from the from physics in general. And you can think about Hamiltonian for purpose of this talk. You can think about the Hamiltonian as a function that returns the energy of a quantum system as a function of the state of this quantum system, right? So now we can also prepare a simple Hamiltonian and we can initialize it to the ground state. So for example, this can be just a superposition of all possible states, right? So we can use something that is called the Hadamard gate or many Hadamard gates to prepare such a simple Hamiltonian easily. And then if we evolve this simple Hamiltonian, or in fact, the quantum system corresponding to the simple Hamiltonian in adiabatic way, so according to the adiabatic process that we have defined, and then this quantum system is evolved to another quantum system that corresponds to the desired complicated Hamiltonian corresponding to our optimization problem. Then by the adiabatic theorem, the system remains in the ground state. So at the end, the state describes the solution to our problem. So there is a hope that in case of such computations, if we evolve one quantum system, for example, by modifying the strength of the magnetic field, we can just end up in another quantum system for which this low energy state will correspond to the solution to our optimization problem. And if we do it in an adiabatic way, we can be sure that this solution will be optimal in general. So Besides doing this evolution in adiabatic way, we should also ensure that we do this evolution slow enough. And there are also some mathematical formulas explaining how slow we should do it, but I can tell about it later if there is an interest, of course. So now there are at least two interesting questions. So the first question is how to define or how to find this complicated Hamiltonian that would correspond to our optimization process, our optimization problem that we want to solve. And I will tell how to do it just by presenting an example of how we did it in case of this vehicle routing problem. And another question is whether this, let's say, adiabatic computations or how they can correspond to, let's say, circuit-based quantum computing models that can be solved or executed on some other quantum computers like IBM machines, so quantum computers from IBM or Rigetti, for example. So it has been proven that this adiabatic quantum computing is polynomially equivalent to this conventional quantum computing in the circuit model, which is good because it means that these computational models are more or less equivalent. But the problem with adiabatic quantum computing is that it's not easy to do it, to just ensure that we have the adiabatic process in the real world. So instead of just running or executing computations that will be run according to this adiabatic definition, we could run something that is called quantum annealing. So anyway, we can just also modify the strength of the magnetic field, evolve our simple Hamiltonian and get another Hamiltonian, more complicated Hamiltonian at the end. But the problem is that we cannot be sure at the end that the solution or this low energy state or lowest energy state will correspond to the optimal solution of our optimization problem. So that's why we cannot be sure that we'll be able to solve NP-hard problems on quantum computers, or at least on adiabatic quantum computers. At least it hasn't been proven yet that we'll be able to do it. But at least there is a hope that maybe these quantum annealing approaches could be used as another heuristics or meta-heuristics solving some difficult combinatorial optimization problems. So here is also another visualization of this quantum annealing process, right? So we have this, first we have this simple Hamiltonian that is easy to prepare. And finally, we have the final Hamiltonian that should correspond to our optimization problem and also correspond to something that is called the Ising model. So I will also tell about this formulation soon. And then by modifying the strength of the magnetic field, we also modify our quantum system and we modify the Hamiltonian that we have. So initially, we were in the lowest energy state of this first initial Hamiltonian. And if we do this evolution in adiabatic way, then according to the adiabatic theorem, we'll stay in the ground state that would correspond to the lowest energy state and the global minimum of our optimization problem. But as I said, since we are not able to ensure that we have these adiabatic computations, we can perform only quantum annealing, and then we cannot guarantee that the solution, that the slow energy state that we find at the end is indeed the lowest possible energy state. But at least there is a hope that this solution will be, let's say, good enough for our needs, right? And maybe if we just repeat these computations many times, then it's quite likely that after many trials, we'll find quite good solution to our problem. So that's the idea. Okay, so I said that there is something like the Ising model or Ising model, because probably that's the correct correct pronunciation. So this Ising model is a model of ferromagnetism traditionally used in statistical mechanics. And here we have variables, binary variables that correspond to spin up or spin down. So these are just atomic spins or magnetic dipole moments, right? And we also have some relationships between the spins represented by couplings So these are correlations or anti-correlations, and now we have the objective function. This is the Hamiltonian of this ferromagnetic. That can be expressed as follows, right? So we have these binary variables, we have some parameters, and in general, this is something like a square form, right? So these binary variables can be multiplied, but anyway, the sum of the exponents can be only at most 2 in this case. And in mathematics or in theoretical computer science, there is also something that is called QUBO, or quantum unconstrained binary optimization. So here we also have binary variables. So in this case, they correspond to values 0 and 1. And as you can see, we also, so in this QUBO optimization, the goal is to find the minimum of the function that is expressed in such a way, right? So again, we have binary variables. We have the degree at most 2, right? And we have some parameters. So we can see that there is a correspondence between this Cuba formulation and the Ising model, which means that if we are able to just define our optimization problem as or using this Cuba formulation, then we can later just translate it or encode it into a physical system like a ferromagnetic and perform this quantum annealing, let's say, right? So this is how we can do it, and as far as I know, this is how it's implemented on quantum annealing machines from D-Wave company, at least. All right, so now coming back to VRP and its variants. So yeah, this is just a recall of the definition of VRP and variants of VRP and the traveling salesman problem. And now how we can solve these problems using quantum computing, using quantum annealing. So first we have to introduce some variables and introduce our notation. So let's assume that we have M vehicles, M trucks that we can use. So this is our fleet. So we can imagine that we are a logistic company and we have a fleet of up to M trucks. And we have to visit up to N or exactly N customers, right? And they are just located in different nodes, different vertices in our graph. And we also have the special node in our graph that is our depot. So that's the starting point and the final destination of all the trucks. We also have costs of traveling from node I to node J, right? So we assume that the cost of staying in the same location is 0. But for all other edges in the graph, this cost should be non-negative. So this cost can correspond to time of travel or the distance or the value of money that we need to just travel from one point to another point, right? So this is our cost. So there might be different interpretations, of course. And finally, we introduce our binary variables. So as you can see, here we have 3 indices, I, J, and K. So I is the element from the set T. So this is just an identifier of our vehicles, our trucks. J is from V. So this is the identifier of our vertices in the graph. And K is also from the set of identifiers of nodes with 0 as well. So this binary variable should be equal to 1, or if this binary variable is equal to 1, it means that in a given setting or in a given solution that we can, for a solution to vehicle routing problem instance that we can just define using these binary variables, the vehicle I visits the node J as kth location on its route, and otherwise this value should be equal to 0. So now some observations. So for each vehicle I, xi n plus 1, 0 is equal to 1, and for lower values of J, it should be equal to 0, which means that the depot, so again, n plus 1 is our depot, identifier of our depot. The depot is always the initial location, right? So at the time point 0, we are always in the depot. So we start in the depot. All vehicles are in this initial location. And also, if for some L we visit the depot again, then we assume that our vehicles just stay in the depot, right? So the depot is always the last location on each route. All right, and here is the Cuba formulation. So it may look difficult, but I will try to give an intuition of how to think about it. So as you can see, we have these binary variables that we defined here, right? So xijk is equal to 1 if in a given setting the vehicle I visits the node j escape location on its route, otherwise it's 0. And we also have the costs of traveling between various vertices in our graph. So this first component, so as you can see, we have 3 components in this sum, right? So the first component is a sum of all costs of travels from the depot, right? So here we have the depot. So we travel from the depot to any other node in our graph. And this node is the first location on our route. So in the time step 0, we were in the depot, but in the time step 1, we are in location n, right? So that was the cost involved here, right? So this is the cost of traveling from n plus 1 to n. So this sum is just a sum of all the costs of travels from the depot to the first visited node for all vehicles, as you can see, right? So we have the sum over all vehicles. The second component is a cost of the last section of a route. So this the travel to the depot in a special case when a single car serves all n orders. And only in such a case, this component can be greater than 0. And the last part is the cost of all other sections of routes, right? So this is our Cuba formulation. So assuming that we have we assign some values 0 or 1 to our binary variables, we can calculate the cost of a given solution. Okay, but if we just focus on minimizing just this cost function, we can easily see that the minimum is just equal to 0, right? So we can just assign the value 0 to all these binary variables that we have here, right? But in such a case, we don't visit any node, right? So now we also want to introduce some additional constraints that should be satisfied in order to ensure that the solution found by our solver or by our algorithm, by the quantum annealing, will be just a valid solution, right? So this will be the valid solution for the vehicle routing problem. So how to ensure it? So first, we define function that is the binary function, and so the values can be 0 or 1, and the minimum value is equal to -1, as you can see. And this minimum value can be achieved only if exactly one of these binary variables from yi to yn is equal to 1. So only in such a case we achieve the minimum of this function. Okay, so now we want to add some constraints. So we want to minimize another sum here, right? So here, as you can see, we have the sum over k, so over all the nodes that should be visited. And here we have all the vehicles and all the, let's say, orders, right, of visiting a specific node. So what does it mean that we want to minimize this sum? So minimizing this sum means that we want to make sure that the value of this function a will be equal to -1 for all our nodes, which means that for all the nodes, or each node is served by exactly one vehicle and exactly once, right? So this is the condition that will be satisfied if the function a, or this component, just achieves a minimum value. And by analogy, in this case of the second component, the minimum of this second component corresponds to the situation in which the value of a is equal to -1 for all m and all n, which means that each vehicle is in exactly one place at a given time, right? So for a given vehicle and for a given time, only one of these, let's say, x variables, binary variables, can be equal to 1 or should be equal to 1 in order to ensure that this component will get or will have the minimum value. So now we know that beside minimizing our cost function that we have defined here, right? We also want to minimize another function that will correspond to our constraints. So now if we set the values of these constants a1 and a2 to be, let's say a1 should be relatively slow and relatively small, and a2 should be relatively large, so that if this value a2 is large, then we can be sure that the minimum value found by any algorithm, any optimization algorithm, corresponds to the situation in which the value of Q is minimized, right? So we want to ensure that the value of Q will be minimized, which will mean that that our constraints, all our constraints, are satisfied. And after satisfying all the constraints, we also want to minimize our cost function, and this would give us a relatively good solution to our optimization problem. Okay, so that was the first approach, and how we can optimize it. So we can assume that all vehicles serve approximately the same number of orders. So let's say up to A plus L deliveries, where A is the total number of orders divided by the number of vehicles. So this is the average number of orders or customers that should be served per vehicle, and L is just a parameter, right? So in this case, we can say that we assume that we want our fleet to be evenly loaded, right? So that each vehicle should take more or less the same amount of some goods that should be delivered, or visits more or less the same number of customers. And after introducing such an assumption, we reduce the number of binary variables, and this may also simplify our computations. There is another algorithm that we invented that is called the DB-scan solver. So without maybe going into details, I can say that first we employ a clustering algorithm that just first clusters all the nodes, all the customers in our graph into some subsets, and in each subset, for each cluster, we just solve the instance of the traveling salesman problem, assuming that all the nodes or the customers in a given cluster should be visited by just exactly one vehicle, right? So this is just the idea, and there's another algorithm that is called solution partitioning solver, or SPS in short, in which we first calculate the route using any algorithm solving traveling salesman problem. So it can be our full Cuba solver that we have defined, and then we just divide this solution into clusters. So in this algorithm, and in the original implementation that we use, and for which I will also present the results of experiments, this clustering was performed, or division of the solution into smaller parts was done using dynamic programming, and there was also an optimization part involved, but I can just tell about these details later in the Q&A session, because it's more complicated, let's say. So I'm not sure if all of you are interested, but anyways, I will also later give a reference to the paper in which all these algorithms are explained in details. Okay, so having these four different approaches to solve instances of the vehicle routing problem, we started running some experiments. So the goal was to compare the results of different algorithms, both quantum algorithms and also classical algorithms, on several data sets. So for this quantum or hybrid quantum classical algorithms, we ran experiments using D-Wave's LEAP platform and two solvers. The first one was QB-Solve, which is a quantum solver that can be run on quantum processing unit or CPU, assuming that we just simulate this quantum annealing algorithm on the just classical processor. And there was also a hybrid solver that used or was using both quantum and classical processing units at the same time. And in case of classical algorithms, we tested several algorithms that can be found in literature, like simulated annealing, B algorithm, or evolutionary annealing. We also prepared two datasets. The first one was based on Christofides dataset, which is a standard benchmark for capacitated vehicle routing problems, and it's well known and frequently studied by the scientific community. And we also built our own dataset based on a realistic road network of Belgium, acquired from the OpenStreetMap service. So later I will tell why we use the road network of Belgium close to Brussels. Okay, so this is just a description of this crystal fitted data set. So we have different number of vehicles, different capacities, different number of orders. And we also had different number of orders, different locations for the second data set based on realistic road network. So here are the results of experiments, and we are just getting closer to the end. So first we run experiments on the smallest possible data sets that we had with only 1, 2, or 3 vehicles. And it turned out that even for such cases, it's difficult to obtain a good solution by running our quantum algorithm on quantum processing unit. So we can get good solutions when we just use a simulator of this quantum annealing, but that is run on a classical processor, or when we use the hybrid approach, so both classical and quantum processors at the same time. It was similar in case of this average partitioning solver. That was our second algorithm. And in this case, the results were still similar, let's say. But then we started running experiments on a bit larger data sets, so also with 3 vehicles, but with more nodes, more customers. And then it turned out that we can observe the advantage of this average partitioning solver in some cases. And we also tested the DBSCAN solver. So that was the third solver that I introduced. And again, the results were quite good. So we ran experiments on even larger data sets. And for even larger data sets, we achieved better results using this third solver, the DBSCAN solver, in which we first cluster all the customers or the nodes in our graph, and then just execute the algorithm for solving traveling salesman problem in each of the clusters, right? And finally, we run experiments on even larger data set in which we compared this DBSCAN solver, which with the solution partitioning solver, in which we first find the solution for the traveling salesman person problem and the traveling salesman problem, and then divide the solution into several clusters, let's say. So it turned out that this solution partitioning solver can outperform the DBSCAN solver, but both algorithms were run on just simulators of this quantum processing unit. And finally, we also used some other data sets just to compare the solution partitioning solver with the classical algorithms. And it turned out that these classical algorithms can still produce better solutions in most cases, but in some cases, our hybrid quantum classical solver can outperform at least one of the algorithms that we have here. And it was also interesting to run experiments and compare these algorithms on Christofides dataset. That's our standard dataset, because all the datasets that I've mentioned so far were generated based on real road network data from Belgium. But here we used the standard benchmark dataset. And it turned out that this hybrid quantum classical solver is able to achieve comparable results to the classical solvers. In some cases, it can outperform the classical solvers. In some cases, the classical solvers can give better results, but in some cases, the classical solvers are also not able to find good solutions. So in general, this hybrid solver was not bad, let's say, on the benchmark benchmark data set. So now some conclusions. So the first conclusion was that it doesn't make sense to run experiments just on quantum processing unit, especially for large test cases, because this is just due to the noise and also the number of qubits that we need. So we can use just simulator of quantum annealing on CPU, or we can just use this hybrid solver. Among this hybrid or quantum algorithms, the solution partitioning solver gives the best results. We compared it with these classical heuristics or meta heuristics, and usually these classical algorithms still give better results, but in some cases on some benchmark data sets, the results are comparable at least. The code that we use for experiments is open sourced, so it's available in the official repository from D-Wave examples. So you can check it out and maybe also use the code to develop it further if you are interested. It's available under the MIT license. And we have also some interesting plans for the future work. So I've mentioned that so far we've run experiments for or that solved only instances of VRP or capacitated VRP, but we would also like to add this time window constraint, right? So at time windows in which our customer should be served. We want to investigate for which scenarios the hybrid or quantum algorithms give the best results comparing to classical algorithms. So to answer the question for which scenarios we may expect some advantages in the future. So the idea is, or the intuition is that, okay, we can see that in some cases, in some data sets, the results achieved by these quantum or hybrid algorithms are closer to the best results achieved by classical algorithms, but in some cases, the differences are still relatively high. So maybe there are some patterns in the data sets, and maybe that's something that we should analyze with the hope that maybe there are some special instances of the VRP that for which we may expect some advantages in the future, assuming that we'll have more qubits or lower noise, a better fidelity of our quantum machines. We also want to investigate algorithms using circuit-based quantum computers like QAOA or VQE algorithms. So basically, it's variation quantum algorithms. And in fact, this is also the research that we've already started. So we've run some experiments, but only for relatively small instances with up to 5 nodes. This is just due to the fact that in case of the circuit-based quantum computers, we still have relatively small number of qubits available. But we can think about scalability of these approaches, and we are also investigating something like graph coarsening or graph partitioning approaches, in which we want to divide the large instance, the large graph that we have, into smaller subgraphs, and these smaller subgraphs can be solved. Or for these smaller subgraphs, you may find or just search for optimal or suboptimal solution using hybrid or quantum algorithms, and then we may want to just combine the solutions for smaller instances into just a solution for the larger graph. There are also some works done by my team in which we use quantum neural networks and which we use surrogate optimization, so some kind of quantum machine learning approach. In the surrogate optimization, so in case of quantum neural networks, the idea is similar to using variation quantum algorithms, but basically we just so in this variation quantum algorithms, we have something like ansatz. So this is just a special circuit, quantum circuit, that we parameterize in order to just estimate the quality of a given solution and produce better solutions for our optimization problem. And the idea is that just to also use the neural networks to basically just to find or estimate the quality of given settings better. And there's also something like surrogate optimization in which we want to find best values of the parameters in the Cuba formulation. So I mentioned that when we build this Cuba formulation, we have a component corresponding to our cost functions that we want to minimize, and we also had a component corresponding to satisfying our constraints. And then there is a trade-off, right? So whether we want to have or be certain that that all the constraints are satisfied, but maybe we may allow that some constraints are not satisfied with a small probability, but at the same time, thanks to this, maybe our solver will be able to find a bit better solution. So that's the idea behind it. Okay, so this is work in progress, basically. So I said that these are future plans, but in most cases, it's already work in progress because I'm now collaborating with almost 20 people from many countries. So most of the results that I presented are also included in the research article that we published 2 years ago at the ICCS conference. So the title is New Hybrid Quantum Annealing Algorithms for Solving Vehicle Routing Problem. It was co-authored by several researchers from the University of Warsaw, but now we have also researchers from India, from Spain, from Morocco as well, one person from Canada, from Toronto. And this research was carried out within the frame of the project that was called Green Last Mile Delivery. So the goal was to optimize the last mile delivery And our partner, or one of our partners, was the Coilert group from Belgium, and that's the reason why we also performed. We conducted experiments on the road network of Belgium close to the Brussels. And other partners were University of Cambridge from the UK and Technion from Israel, from Haifa.